All right, so the next talk is from Haggai Landa from IBM Quantum, who unfortunately can't be here in person after all, who's going to tell us about stabilizer dynamics with IBM quantum devices and error correcting modeling. So over to you, Haggai. You got 25 minutes, then we'll have 5 for questions.
Great, thank you very much. Please let me know if the contrast is not so good in the presentation. So I'm from the Israeli quantum computing team of IBM Quantum, and very unfortunately, I had to cancel my arrival in the last minute, and I wish I could be there in this great venue, but I'm happy to be able to present this remotely. So this talk is composed of 2 parts mostly. First, I will describe experiments that can be done on IBM quantum devices, noting the complaint by Aaron, and also simulations of those experiments. And these are about dynamics of stabilizers, of graph states, of many-body qubit states that we were able to probe experimentally and simulate in software. And talking about dynamics of stabilizers takes us quite naturally to the second topic that I'll cover, which is what happens in error correction modeling when we consider realistic noise models of the qubits that we have and many other qubit systems. Good. So let's see. Why doesn't the slide move on? Okay, now I get it. Great. So IBM fabricates qubit devices, superconducting qubits, and deploys and makes publicly accessible many of them. They can be accessed on the cloud. This is the website where everyone can go and even without signing in, see some of the devices, not all of them, and a lot of the properties for each device. Many devices have 127 qubits. These are known as Eagle devices. There is a topology map, a connectivity map of the qubits on the web page that you can check. And there are many parameters. For example, I'm showing here the T1 and T2 median values, and also values that are obtained for each qubit at calibrations. And in the background, you can also see most of the talk will be focused on qubits in those Eagle devices, which are actually the previous generation. The newer generation is called Heron. These are much better qubits, and they will be the types of qubits that will continue to evolve for the next few years. But what I will cover is essentially about the Eagle qubits, and just towards the end, I will discuss a bit dynamics more relevant to the Heron qubits. Okay, and I should mention that registered users can get free time to execute experiments on those Eagle devices via the cloud a few minutes per month for everyone who registers for free, and you're welcome to try and do it. Great. So the physics of the superconducting qubits has been mentioned a bit in the morning. There are capacitive elements, inductive elements. There is the superconducting phase, which sits here in the cosine in the Hamiltonian, and the conjugate variable, the number operator of Cooper pairs, which constitutes this fundamental Hamiltonian of each qubit. If one expands the cosine in a Taylor expansion and goes to second quantization, this is the typical transmon qubit Hamiltonian. There is a harmonic frequency, which is of order 5 gigahertz, maybe a little bit less or more in the lab frame. And there is a nonlinearity. Since this is a cosine potential, we're getting a softening nonlinearity term in quartic order, which means that the level 2 is actually closer to the level 1 than the gap between the 0 and 1. The order of magnitude of the difference is about 300 megahertz. Can be compared to this 5 or 4.5 gigahertz gap. But these are the qubits that we have. If one restricts to the qubit to the 2-level manifold, the Hamiltonian in the lab frame is just omega times 1 minus sigma z. And to this, to each qubit, we add an RF line, which allows to perform the rotations, the single qubit driving. So there is a sigma X term in the two-level Hamiltonian with a microwave frequency, which is controlled phase and driving amplitude or intensity or frequency in terms of Rabi frequency. And as was asked before, I think there is an interface for running dynamical experiments and controlling all of these parameters from software using time-dependent pulses. So there is a programmatic control over time discretization values for these parameters. And this is what allows us to run all of the experiments that I will describe actually via the cloud. I'm not an experimentalist by background, but today I can do a lot of things remotely. If one goes to the microwave reference frame, and the microwave might not be exactly calibrated to the qubit frequency omega due to a detuning error known or a drift, a calibration error between the calibration and the actual qubit frequency. Then in the rotating wave approximation, we have this Hamiltonian, which has delta as the sigma z term and omega multiplying the sigma x and sigma y terms. And these are the terms, these are the parameters that we often control. Good, so the first thing, the simplest thing that one can think of doing with a single qubit is to do a Ramsey experiment. We start with the zero state, which is the up state in physics jargon, right? Pointing along the north pole of the Bloch sphere. We rotate it to put it in the plus state along the equator, along the x-axis, and waiting a varying delay time tau, we are measuring the projection of the Bloch vector x and y component. These are the expected or typical plots that one sees in a Ramsey experiment, composed of a rotation in this frame with frequency delta, this detuning, this small frequency delta, which is typically of order a few tens of kilohertz, up to a few tens of kilohertz or a few kilohertz, and an envelope of exponential decay with T2 rate, which is, as we saw before, 100 or 150, 200, depending on the qubit. Between 100 and 200 microseconds, depending on the qubit. Great. But sometimes we run those experiments, and what we are seeing is completely not the expected decay curve, but they're within, sometimes here in this example, a very high quality qubit with a few good 100 microseconds of T2 decay envelope. We see two frequencies, we see bits, okay? If I want to take this data and plot it in a different way, here, what I'm plotting with red dots is the experimental, of course, a projection of the qubit's Bloch vector in the xy plane. Okay, so the magnitude of the sometimes called draw coordinate, right, in the in the equator plane, and we see that what it does, it actually goes down, goes to zero. So the qubit component in xy plane goes through zero and comes out on the other side, goes up again and oscillates like that, going through zero length. Since we are taking as control the z expectation value, we are seeing that the magnitude of the Bloch vector does not go to the z component. So it looks like it's a non-Markovian dynamics if you're coming from some community. One might think that the qubit is being entangled with some other degree of freedom around, but that's actually not the case. There is a phenomenon that is somewhat well known, but often also misregarded, which is related to the fact that actually the 0 and 1 states, the qubit states of the Cooper pairs, are actually split. Each of them is split into two states. The splitting of the 0 state is quite negligible and can be neglected in our experiments, but the splitting of the one states, of the one state, the excited state, the qubit level, into two states. It depends on the parity of the number, basically the number parity of quasi-particles, excitations of the qubit, of the superconducting wave function that are tunneling in and out of the qubit. So this splitting is, for example, in this reference, has been controlled by a charge offset that allows to shift, in units of a Cooper pair charge, 2 electron charges, it's periodic. So by putting a charge that offsets it, this splitting can be measured, and here it's been of order of 2 megahertz or something like that. It's quite easy to measure or relevant in some dynamical regimes from this experiment 10 years ago. But actually in our current qubits, due to the parameters of nonlinearity, this splitting is of order of tens of kilohertz in the Eagle devices. And the nature of this dynamics turns out to be the following. During one experimental shot, between initializing the qubit and measuring it, and I remind you, I'm still thinking of a Ramsey experiment with a delay time of a few tens of microseconds. Within one experimental shot, or within most single experimental shots, the number of quasi-particles on the qubit is constant, is fixed, is either odd or even. There is no tunneling in or out, and it's actually randomly distributed between all the shots. So there is a 50% chance in each experimental shot to have either an even or an odd number of quasi-particles, which means in approximately one half of the experimental shots, the qubit will have an omega even frequency, which is slightly higher by a quantity nu than the other half of the shots in which we have like omega odd, of course, even an odd are arbitrary labels, with a frequency which is minus nu. The mean frequency is delta, the detuning error that we have. And then this causes these oscillations in the measured expectation value of the Bloch vector in the xy plane. Right now, we can think about it that in each shot, we have put the qubit along the x-axis, but in half of the shots, there is an extra new frequency, making it rotate in the positive direction. In the other half of the shots, it rotates in the negative direction. After a delay, which is equal to pi over 4 of nu, like a quarter period, in half of the shots, the qubit will be pointing along minus y, in the other half along plus y. And so when we take expectation value over shots, this is why we see this apparent shrinking, disappearance of the Bloch vector in the xy plane, and its reappearance as a function of the delay. Good, so after we've clarified this mechanism, I'm going to, is there a question right now? Okay, so probably not, although there is some static noise. I'm going to make a big jump, and I'm going to say what I want to do with this noise, not with this noise, with this characterization of the qubit quasi-particle frequency, nu. So what we're actually going to do in this experiment and simulation, it's quite a dense slide, so please don't read it as it is, just follow me. What we want to do is take 12 qubits on the device. They have this ring topology, indicated here by the blue circles. Create a stabilizer state of a graph state that corresponds to this connectivity. So a graph state is created by putting all 12 qubits in the plus state, and then doing a control Z, a CZ gate, between each qubit and its neighbor state. This is a graph state of this 12-qubit ring. It's characterized by 12 stabilizers. This graph state G is characterized by 12 stabilizers, so 12 operators of this form, ZXZ, each of which, acting on G, leaves it invariant. So there is one unique state, quantum superposition entangled state, entangled state of this form, and this is the graph state of 12 qubits. Now we want to create it in experiment. It's not so, it's quite straightforward, putting all the qubits in the plus and doing the CZ gate. And we want to simulate the decoherence of this graph state of this many-body 12-qubit state. Now, we have a problem. We have in half of the shots of the experiment, we have qubits having random, I mean, not in half of the shots. Each qubit in each shot of the experiment will have either plus or minus a detuning of its frequency due to the quasi-particles going in and out. But we have a way to simulate this in a many-body simulation. We attach a fictitious qubit, call it sigma tilde z, to each physical qubit, sigma zi, and we attach this fictitious qubit. We put each fictitious two-level system, this such qubit, into a fully mixed state, so an equal mixture of up and down, right, of 0 and 1. And we shift the frequency of the qubit, of the physical qubit, by nu times this operator sigma z of the fictitious qubit. So this causes in the density matrix a mixture of all these combinations where each qubit in a specific shot is shifted by plus or minus nu at the same time. So we're simulating the dynamics of the density matrix that we have created, initialized with the graph state, and this is a trick that allows us to simulate such a large multi-qubit state. Good. So I'm tracing back a bit here. What we're going to solve is this master equation for the dynamics of the density matrix. The master equation describes the behavior of the system as a function of time. There is the Hamiltonian part, and then there are the dissipative or jump operator parts, Lindbladian parts also known, that describe the incoherent noise. The single qubit Hamiltonian consists, as I already described, of the detuning error, the drift in the frequency of each qubit, and the magnitude of parity of splitting of its excited level. Each of those is about of order up to a few tens of kilohertz, few kilohertz up to a few tens. Now I'm adding another ingredient, which is well known in the community. It's one of the main problems or causes of error or errors between qubits, which is the crosstalk. So in superconducting qubits, qubits that are connected to each other are coupled by sigma z interaction, crosstalk, here quantified using this zeta coefficient, which is again of order of up to a few tens of kilohertz in those qubits. And we have T1, basically T1 and T2 jump operators. So an incoherent operator taking each qubit from 1 to 0, this is T1, and the dephasing sigma z operator that acts on each qubit. And all of this dynamics is being simulated as a function of time. The trick that we are using here in order to be able to simulate the density matrix of 12 qubits coupled together with 12 fictitious qubits, which is equivalent to a simulation of 24 qubits in a density matrix simulation, a noisy state, which is equivalent to the simulation of 48 qubits in a pure state, is to use matrix product states, which can handle efficiently these large Hilbert spaces when the amount of entanglement is not too large. And now, these are the experimental results. What is being shown here are the 12 stabilizers. I've hidden one of them just in order to put again a depiction of the qubits on the device. And these are the dynamics of the 12 stabilizers of the initialized graph state for time up to 50 microseconds. There are experimental points, and there are curves that come from an ab initio, very fancy word, simulation. So the curves are not fitted curves, but they come from fitting the simulation with the characterization of the noise model of each qubit. Let me go back. The single qubit parameters, the 2-qubit crosstalk, the incoherent parameters, T1, T2, measured, characterized for each qubit separately, and something that I didn't mention, the state preparation and measurement parameters, which include each qubit's initialization error 3 parameters because each qubit starts in a state which is close to the ground state, the 0 state in the Bloch sphere, but can deviate from it slightly due to initialization errors, and also readout errors, which give another 2 parameters. And all of these characterized parameters are being fed into the simulation, and we see for most stabilizers, the simulation captures pretty well the dynamics of the stabilizer. The dynamics of the stabilizers are quite, interesting, I would say. They are oscillatory. In some cases, they go to negative expectation values. I just want to mention that these are expectation values of the dynamics of each stabilizer. And in some cases, there are the simulations, the experiment is actually deviating notably from the simulations because of some characterization errors that did not make it. People that have experience in characterization of qubits know that actually not all parameters are all the time stable. So having being able to characterize 12 qubits with all of their parameters, noisy dynamics, is not so it's not so stable, a bit fortuitous. Okay, it's a bit hard to always succeed. So I want to mention or stress that although what I find interesting in this plot is the fact that it is possible to characterize and then simulate the dynamics of this kind of many-body state of 12 qubits for a few tens of microseconds on these superconducting qubits. This model is only a first-level approximation, a 0th order model, let's say, or something like that. And there are always terms that are more complicated. There are always drifts and uncontrolled interactions with degrees of freedom. And it's only a starting point, but it's a useful starting point. And to move forward, I will say that for some of you, perhaps looking at these oscillations in the expectation values of stabilizers that come from these Hamiltonian coherent dynamics, of course, because they are the cause of these oscillations in the qubits, may hint at the possibility to do dynamical decoupling. And if we do dynamical decoupling on the same qubits in the same experimental in the same experiment, we see that actually, indeed, again, experiment and simulation curves, which are not fitted, but just taken from the simulation with the qubit parameters, agree quite well for many qubits. The oscillations that come from the coherent dynamics are almost completely vanishing. What remains behind is an exponential decay due to the incoherent dynamics. For some qubits, we see that the dynamical decoupling is not working exactly as in the simulation because we have leakage, for example, from the qubit manifold, which is not simulated here. And sometimes the gates that apply the dynamical decoupling, of course, are not perfect. And that's the reason for some of the deviations. This dynamical decoupling pulse actually cancels also the crosstalk, the ZZ crosstalk of the qubits. Okay, good. So how much time do I have for the next topic? Probably not enough. Maybe
probably not enough. Probably about 1 minute.
Okay, great. So in 1 minute, I will say just one word about where we take this model of the noise dynamics. And this was a question about does the often employed Pauli noise model, which is often employed, for studying error correction, dynamics, thresholds, understanding, modeling of error correction, how good is it actually? A Pauli noise model that is much more simplistic than a continuous dynamics that is what the qubits actually feel. So I will skip a bit the references here and the results, and we'll just show kind of a main slide here, which is only simulation using a dynamics quite similar to those that I've mentioned in a simplified code. studying error correction cycles for up to 20,000 cycles, and modeling the dynamics using two approaches. Basically, one is a Pauli approximation, that is the green curve, and one is actually following the dynamics of the Lindblad equation. And we see that what is being plotted in green is the failure probability obtained from the simulations. For the Pauli model, it turns out that after about 200 cycles of error correction, in a very simplistic model, which is the code capacity noise, which is extremely simplistic, and yet we see a striking underestimation of the failure probability between the Pauli model and the orange curve here, which is the full dynamics of this code. And this is due to the presence in the density matrix of coherence between the ideal state and the orthogonal logical state to it, which is completely lacking in the Pauli approximation and cannot be seen, but is something that can grow up to significant magnitudes when one follows the Lindblad or the coherence dynamics and does not exist in a Pauli model. Okay, I will finish with that slide that gives some links to tools that can be used to run experiments in this kit, simulate dynamics, and simulate tensor network solver for Lindblad dynamics, and the references are here. Thank you very much.